ideas and initiatives, and I think that this is probably one of the breakthrough ideas that we can have for not just agriculture but global climate change. Therefore, without further ado, ask you firstly, sir.
Thank you very much. Thank you. Well, look, thank you very much for having me in India. I'm very, very grateful to be here. First time I'm here. I was previously a scientist in CSIRO, a soil microbiologist working in forestry, tropical crops and pastures, soils, and then I worked for a long time in our government at a senior level on innovation and innovation strategies for the future. And in a sense, that epitomizes what we're up against, because all over the world there's...
Can I just take 1 second? Can I request everybody sitting that side to come and occupy these chairs here? The board is closer, and I think so all those sitting in the back, let's just occupy these chairs.
Yeah.
No need to waste good real space.
And basically, that realization that there are now 7.5 billion of us on the planet, there will be up to 10 billion by mid-century, and we really have a fundamental challenge. How do we actually find the food, the habitat, the stable environments for that future? But it all depends on water, because life needs that water. And in a sense, this next decade, 2020 to 2030, will be the crisis point, the crucial decade for water and how do we address water globally, everywhere. Australia, the driest inhabited continent, is drying. We're losing up to 30% of our water in southern Australia. Farming systems, farmers are under stress. They used to get 4 reliable crops out of 5 4 crops out of 5 years. Now they're down to 2 out of 5. So economic viability of farming is under extreme stress. So we need to have a new solution. Excuse the pun, water. We need water. How do we secure that water? And so 15 years ago I retired, and as we heard, I formed an organisation with very, very innovative leading farmers Australia-wide, looking at innovations. What do we do to rehydrate, to regenerate landscapes? And then Michael Jeffrey, Major General Michael Jeffrey, our ex-Governor General, also retired, and again he fully came on board because they recognised the strategic imperative globally. We need to secure water to secure basically a future for everybody. And so that became the issue. We need a new agriculture. We need to redesign how we manage water, nutrients, to produce the food in a resilient, sustainable way for the future. And so basically we then said, how can we do this? And of course it's very, very simple. And this is the good news, the very good news, that basically nature actually created this biosystem that we depend on through creating soils. Because soils are the crucible for all terrestrial life, and those soils provide the water, the nutrients that we all depend on for all our food, all our hydrology, our climate, and our future. And so the mission became, how do we regenerate the Earth's soil carbon sponge? Okay, so how do we actually ensure that the water that we do get from rain is not wasted, but is actually able to be infiltrated, captured, retained, and then made available for 365 days of the year to sustain green growth for our food production. So, as in nature, can we regenerate the Earth's soil carbon sponge? So the question comes, what is a sponge? and it's easiest if I perhaps explain just drawing it. 420 million years ago, there was no life on land. We just had oceans and rock. And rock is made up of basically mineral particles. And of course, this contains different nutrients, calcium, phosphorus, zinc, etc. There's 33 plus essential nutrients that we need for life, for our nutrition, our health. But of course, rock is not able to absorb water. So rain falling on that rock will just run away. And what happened 420 million years ago, basically fungi from the edge of the ocean grew up from that estuarine edge onto the rock to solubilize these nutrients. And in solubilizing these nutrients, these fungi basically broke that rock up into mineral fragments. And in doing so, it basically created a loose matrix of rock fragments separated in various ways with bits of organic detritus. This is the residual organic detritus from this fungal colonization, the old dead cell walls. And so basically nature created what is the soil carbon sponge. And it's really quite profound, because basically just by separating that rock into fragments and mixing it with 2-3% of carbon, organic matter, we fundamentally, or not we, but nature fundamentally changed the whole basis of life on land. Rock, we know, can be 2.6 to 3.5 grams per cc. That's the weight of rock per unit volume. It's called the bulk density. A healthy soil has a bulk density of 1.1 to 1.3 grams per cc. So immediately we know that this sponge is made up to 60% out of nothing. Actually air. But that's really the powerful point of it, because it is these voids, it is these empty spaces that are really profound. Because now when you have a drop of water falling onto that soil, it is able to infiltrate and provide water from that soil. So that's really the solution. It's actually the capacity of soils to infiltrate, retain, and then make available water in a sustained way that has enabled life to develop on land. And it started initially with the fungi, but then, of course, the fungi formed symbioses with algae to make lichens, and then we had the mosses and the ferns and the liverworts and the cycads and the gymnosperms, the angiosperms, and we had an evolution rapidly of life all over this rock. And at the same time, we had these terrestrial biosystems extending over the 14 billion hectares of ice-free land on this planet. And really, that's how nature created soils, that's how nature created hydrology, that's how nature created the biosystems, and of course we are just omnivores, animals living on those biosystems, fundamentally dependent on these processes still. That's the water side of the story, which we want to concentrate on today, but the same applies in terms of nutrition. There are nutrients, obviously, in rock. They were formed, basically 4.6 billion years ago when the whole solar system formed, but they're unavailable. They're locked up in rock. But the minute they become a sponge, we have these nutrients now available on soil surfaces. And because of those surfaces available, now we have zinc, phosphorus, calcium. These nutrients are now available for uptake by plants. So again, we have vastly increased the biofertility of these soils, again, by adding nothing. not because we've added nutrients, simply because we've made those nutrients more valuable. And so our farming practices, as in nature, can use exactly these same strategies. Just by creating the sponge, we can create the water holding capacity, we can create the nutrition, we can vastly increase the rootability, the capacity of roots to proliferate, so that instead of using 20 centimeters of soil to grow plants, we can use 2-3 meters of soil. So the volume of soil water, the volume of soil nutrient resources that life can now access has increased exponentially. And in CSIRO, we were looking at rainforests on sand dunes, the world's most bioproductive terrestrial ecosystems, effectively on crushed glass, silicon dioxide. Why? Because these sponges and the very efficient cycling of those nutrients were able to sustain those rainforest bioproductivities. And they're the strategies that we can now take into 21st century agriculture to rebuild the hydrology, to rebuild the biofertility, the resilience, and the productivity of our soils. Okay? So this is what a sponge is. It's really, just nothing added to the soil. It's just a matrix, a structural change, creating the water, the nutrients, the rootability, the resilience. And it's done...
Is it the same thing as humus, or are they two different?
Yes. Basically, these particles become humus. So let's talk about that. So really, it is just this detritus. There's various compounds, humus and glomalin, and various fractions. But basically, 2-3% of organic matter, humus, added into these soils, of course, creates a sponge. As we've just sort of said, this humus has to come from the air, because that's effectively carbon dioxide that's been drawn down by plant life to actually add that carbon to the soil. But we'll come into that in more detail a little bit later. So really it is putting that small amount of carbon into that soil to create the sponge that has a very, very powerful effect. Okay, so that's pedogenesis, that's the formation of soils and its consequences into productivity. But we now have a fundamentally big, challenging situation regarding water around the planet. And to look at that situation, we have to really do a water budget, don't we? We have to see, well, what have we got, what haven't we got, and how do we do that? Now, these data are from Australia, but the same proportionate data applies really everywhere. There may be some few percentage points difference, but the same picture is there. So what's important isn't how much rain we get. What's important is what happens to every raindrop that we do get. Okay? So if we take 100 raindrops, the question is, what happens to them? Do we know what happens to every one of 100 raindrops? And obviously, 99% or 99 plus, we know, fall on the land. Actually, this is the rain that falls on land rather than rain on oceans, obviously. But then we basically, to look at the data, 14 out of those 100 raindrops end up in our streams. And 2 drops out of 100 are able to be stored in our dams. Okay, so basically 2 out of 100, that's the capacity of our dam storage, and applies globally. We've built over 50,000 large dams since the Second World War, World Bank, Asia Development Bank funding, enormous investment in concrete and dam infrastructure. 2 drops out of 100. Okay? And it's those 2 drops out of 100, these dams, of course, where we need all our water. 70% of the water is going into agriculture in Australia, about 20% into industry, a lot of that into energy production, because that needs vast quantities of water for cooling, and then domestic water. So there's agriculture, industry, and domestic water. And so 2 drops, and we're fighting over this water. I mean, this is really where the battleground is. How do we fight over those 2 drops out of 100? And of course, this is being a real crisis point, because as we get less water, as we get bigger populations, this is where the stress is. But we're realizing that there's another 86 drops here. Okay? What happens to them? And of course we know all about that. We know that 36 of those drops in Australia basically infiltrate into our soil sponges and are used as transpiration. Okay, now transpiration is obviously plants taking up water back into the air and in the process growing. And of course that's how we get our food. So transpiration is very important, because that's really where our food comes from. But this is in a sense the natural biosystem. But 50 drops out of 100 basically run off in flood flows or evaporate. Okay? And why they run off and why they evaporate is totally dependent on us through our land management. How we manage our land governs whether this runs off or infiltrates. I mean, runs off, evaporates, or infiltrates. And of course, as we've said, that's because of the sponge. If we have a sponge that infiltrates, if we have compacted, degraded, hard soils, it runs off, and then mostly is lost by evaporation. And so the challenge is, right, how do we actually increase the infiltration? How do we increase the infiltration to limit the runoff? This is 25 times the water that's held in our dams. Okay, so rather than building more dams, if we build the sponge, we can actually conserve that water. We can put it into transpiration. And this is a critical point. We'll come to that, the significance of that, and we can extend the longevity of green growth. We can have a green carpet 365 days of the year to sustain food production, resilience, habitat, biodiversity, all the values, all the critical issues that the UN Sustainable Development Goals are calling for, simply through the sponge, this longevity of green growth. Okay, so there's a simple story, right? How do we do that? But it's actually more significant, because water has impacts. You know, water can be very, very impactful, dangerous with extremes. And we can see this if we look at a hydrograph. And basically a hydrograph, you know, all engineers, they use this all the time. It's simply a measure of flow over time in response to, say, to storms. Okay? If we say we have a 2-inch rainfall event, a 50-millimeter rainfall event, just as we're looking what happens to the 100 drops, we ask the question, what happens to that rainfall, that storm event? And if we've got a degraded soil, just say with 0.3% carbon, organic matter, you know, so we've basically got a degraded soil, we'll get a hydrograph that goes something like this. We'll have a massive flood peak, rapid flood peak, and of course this will be a flood. This will erode. This will cost us massive damage and erosion. So that's erosion plus insurance. it has a massive cost in civil engineering infrastructure. The amount of cement and stormwater drains, culverts and diversions that are needed to manage these extreme weather events is enormous. So this is all very, very destructive. And in a sense, as climate change is now impacting, we're not just getting a lot less rain in some regions, but we're getting much, much more extreme rains. So these things become really, really quite pronounced. You know, how do we get these dangerous effects, floods, etc.? And of course, this happens on a whole catchment basis, so a whole river system erodes and degrades, crashes. We can't sustain agriculture there because we've lost so much soil, we've lost so much infrastructure. But something much, much more serious has happened. Because that water has flooded off, we have effectively designed in drought. Okay, it just goes without saying that we've lost the water, it isn't in our soils, so we have a drought. Basically, we go further, once we have a drought, we have a desert, don't we? Because we're really desertifying that country and we're just basically generating death. Death in the living soil, death in the communities dependent on it. Okay, so simply that hydrograph, that degradation is telling us, hey, we've got to avoid that. And the question is, how do we avoid it? And it's very simple. If we just increase that organic matter, that sponge, to say to 3% carbon, as we've shown here, if we just create that sponge, just logical, we'll get a completely different hydrograph. Because now we'll get a graph that'll go something like this. It'll have the same volume under the graph, it's the same 2 inches of rainfall, but instead of all this water running off, causing all this damage, we'll have this water running off. Okay? And so most of our water will be in our soils. So we are actually recharging our in-soil reservoirs. Okay? And it's these in-soil reservoirs that are really nature's dams. Okay? 2 meters of healthy soil with voids, with 60% voids, can readily hold 1 meter of water. Water that's available across the landscape, when and where needed, protected from evaporation, at no cost, at no capital cost. Water that can drive the longevity of green growth, right? This is actually now green. Longevity of green, 365 days green. And of course, this has to become the key parameter for our future agricultural design. Sustaining green growth, resilience. So it's these in-soil reservoirs that are really powerful. We've got colleagues from the UN here, and basically, previously, if we could get a 30% growth response in the Green Revolution when I was involved, we'd be delighted. Okay? But in this situation, this is the length of growing season, isn't it? Now, we've changed that. We've got a growing season that goes all, well, not to infinity, but it just keeps on growing. So instead of having a 2-inch rainfall event and we've got green growth for 10 days afterwards, we've got the same rainfall event and we might have green growth for 200 days. Okay, it's thousands of percent growth response through longevity of green, 365 days green carbon. So that's food production. See, it's not a matter of how fast we grow or whether we have a better genetically engineered plant. If we can extend the length of the growing season, longevity of green growth, it's production, it's more food, it's more resilience, it's more productivity. Okay? And so that's in a sense what the rainforest does. That's why it's so productive, because it's buffered and extended that growing season. And this is in a sense a massive opportunity for 21st century agriculture. How do we use this 365 days green, the longevity of growth, and really use that to drive food futures, social stability, to feed the 10 billion. And it's all possible just through rebuilding the Earth's soil carbon sponge. Yeah.
So in terms of retention of water, I think this is very effective. But when you look at the other sort of ailments that we're dealing with today in terms of agriculture, we have a lot of disease. And what we find is when the moisture in certain areas gets extended for long periods of time, then disease becomes very rampant.
Okay, absolutely. If we have
completed.
Yeah, no, we will complete, but just very quickly. But this fits in here too, doesn't it? Because basically, yeah, if we have a compacted soil, we can very rapidly end up in a waterlogged soil. Too much water. And of course, then you create disease. But if you have a free draining soil, quite the opposite. That water is draining and recharging your aquifers. Okay, it's not sitting there, it's recharging the aquifer. We're in India, water being taken out from aquifers, 1,000 feet. We're down to the very last. The Ogonnella Delta from Nebraska to Texas and America, 80% gone. China's aquifers, 80% gone. California's Central Valley, no more snowpack, no more aquifers. We're all basically down to on our knees or less. Okay, so this is recharging aquifers. If we have the sponge, it's a very positive thing. But let's keep going. So that's 100 drops, but we're now facing a reality that we might only have 70 drops because of climate change. Okay? The unreliability of that rainfall, the extremes. So we've gone from 70 drops, from 100 drops to 70 drops. So now the question is, what will happen to the dams? If we're relying on dams, 2 drops out of 100, how many drops out of 70? So we've got dams like the Hoover Dam on the Colorado River in America, one of the massive dam engineering feats in the 1930s, that will probably never ever be full again. Cactus. Finished. It might silt up, but it will never be full of water. And that's happening to a lot of those 50,000 dams that we've had all over the world. We talked earlier about the Aral Sea, all gone. See, and so the reliance on this surface water, dams, is very, very dangerous, because if we're only getting 70 drops, we become precariously exposed in agriculture, industry, domestic water. So we have to find smarter solutions. And this is, in a sense, what we've been looking at. This is why we're here. We came and visited Andhra Pradesh and looked at systems. Where are there smart innovations? We've got farmers here, again, growing sustainable crops on, 6-8 inches of rainfall. So where are the smart innovations? What has to happen? And one of those questions is, can we actually not have 70 drops, but can we give you 120 drops? Now that's a little bit audacious, isn't it? I mean, sort of, here we are, climate change, and we're now talking about 120 drops instead of 100. And again, we've got to think outside the square. We're looking at a new agriculture. We're looking at a new future. We've got an imperative. Most of us know it, but basically there's 50,000 parts per million of water that's in the air above us. 50 centimetres of water, 5% by weight, flowing across all the world's deserts continually. Rivers of aerial water. The trouble is, with Delhi, it's very clear, the trouble is that most of it is in water vapour or humid haze microdroplets. Microdroplets, haze droplets are far, far too small to fall out as rain or precipitate. But worse than that, haze microdroplet would maintain humidities of dangerous levels of 80–90% above, and when it gets hot, create this humid health risk, because then we can't perspire to cool ourselves. Okay? So basically, there's all this water flowing across the earth. Can we harvest that? Question mark. Can we get to 120 drops? And of course, we then, again, as here, we look at the nature. You know, what did nature do? Can nature harvest it? And the answer is yes, it does, all the time. We've got the sequoia forest, for example, in California. They get 70 to 80% of their moisture from fog and mist condensation on their foliage. We've got the same thing in the Australian desert. You know, we've got salt bushes and other plants that are continually harvesting moisture from that area. 1 to 2 millimeters per night. 1 to 2 millimeters per night. You know, over basically 100 nights, 200 millimeters, 8 inches of rainfall. Hey, we're only getting 100 millimeters in our rain gauge. That's twice our rain gauge measure. Okay, so here is now the question, can we actually harvest some of those rivers of water in the air? Can we design agro-ecosystems that effectively use this water resource? And we came to Andhra Pradesh very much because some very leading, innovative Indian farmers had done something that was really not possible in a way, right? Not possible in a way. They had basically explored the possibility of, can we have pre-monsoon dry cropping? Let's try that one. Okay, so there was a system of pre-monsoon dry seed cropping. And basically in May, they sort of said, look, can we sow seeds? And we actually had seed with a biostimulant that we added. We'll come to that later. And then basically, this is in the middle of summer. And then can we actually grow that seed? Now, in this situation, Andhra Pradesh, they got 40 millimeters in late July of rain. They got another 60 millimeters in late September. And the stunning thing is, through this agro-ecosystem, they were able to grow a mixed cover crop 2 meters high, producing from 12 to 15 tons of biomass per hectare. And so we have this very much germination, and here we have a crop, 12 to 15 tons of biomass per hectare. And it's a paradox, isn't it? Because we know that 1 gram of biomass would need basically a litre of water, through photosynthetic and biochemical processes to grow that 1 gram. So that crop might have just let's say 12,000 tons of water per hectare. That's what the water need of that crop would have been. But we've only had 1,000 tons of water per hectare as rain, okay, over that period. So obviously there's a difference here. And while we need to do more studies and document and verify, and this is really quite challenging or innovative, we believe we know where that water came from. Because with these biostimulants, we were able to get germination of these plants, we were able to get mycorrhizal fungi growing from those germinated seedlings, they were able to get some of this water from these soils, which is unavailable to plants, well below wilting point. I mean, again, this is a situation here that plants can get water from soil, from these free spaces, you know, up to wilting point. But all the soil particles will still have films of water around them at tension way beyond wilting point. And the mycorrhizal fungi that we have stimulated through these switches are able to access this water, these water films. So some of that has come from unavailable water in the soil, soil water, and the answer is, it's a question mark, but probably yes. But the other thing is, because of that water, has it been able to put a shoot up, and has that shoot been able to harvest some of these rivers of water that are flowing across that country in the air? So how much of that has come from actually the humid haze harvesting? Now, as I said, we have got experiments planned, measuring this thing precisely to do the scientific verification of this. But if what we believe happened can be confirmed through this process, this is groundbreaking. This is earth-shaking. Because we are now saying here is a productive crop because of these biological farming practices that is actually able to establish 365 days green cover, productive food production on far, far lower rainfall than we thought possible. Okay? Not only can we grow food, but we can maintain green plant cover and healthy biosystems over time. And that has profound global strategic significance. So really this is now the challenge. Yes, we will verify. Yes, we will do more exploration. Yes, we will document. Yes, also because of the process, we are already extending these trials to thousands of applications where different farmers, different farmer groups are looking at variations, so we will get that body of information, that veracity to sort of say it's not just scientifically feasible, but it applies, yes, we can make it apply throughout agriculture. But if we can do that, this is a profound breakthrough led by India, basically pre-monsoon dry cropping to actually start harvesting this water from the air. Okay? It has another even more profound effect, so we'll cross that sponge out. And this now comes into the climate story. No. Water, no, because, yeah. But look, it's okay. Okay, so we have a landscape. At the moment, our landscape, Andhra Pradesh, with India, Rajasthan's even worse, Gujarat, basically, we might have 25% green and 75% red. Okay, so both in terms of area and time, a lot of our landscape is actually exposed, dry, red soil. Okay? And this is the same in the earth, across the earth. We have, so far, humanity created over 5 billion hectares of man-made desert and wasteland. As we said earlier, only 14 billion hectares of land on this ice-free planet. Some of it will go underwater with sea level rise. 5 billion hectares of man-made desert and wasteland. All hard red surface. Okay? And of course, the tragedy or the danger is that basically this heats up. Where we have green vegetation and growth, we've obviously got a protected soil cover. We also have transpiration. We'll come into that in a minute. Here's transpiration, taking water vapor from these soils and basically turn it from liquid to gas. And of course that takes 590 calories of heat energy per gram of gram of water to turn it from liquid to gas. This is a latent heat of vaporization, inescapable physics. Okay, so these surfaces, soils under these vegetated, protected, transparent vegetated, stay consistently cooler. Very rarely do they get above 20 degrees centigrade. Okay, because this cooling effect of these latent heat fluxes and the protection. By contrast, the 75% red, this bare exposed surfaces is getting sun rays. It's obviously heating up. That's being absorbed by the soil. In Australia, these soils, we measure them 70 degrees centigrade. Okay, but even here you'll have many of them at 50 degrees plus. Okay, bare, you can't walk on them, right? They're just too hot. So vast differences in temperature of the exposed soils relative to protected, moist, transparent soils. And now we have a fundamental law of physics that steps in. Because just as Einstein equals mc squared, there's a law of black body radiators. And it tells us that the amount of re-radiation from a black body, a surface like the Earth, or any stove, is proportional to a constant times the fourth power of the temperature in degrees Kelvin. So what that means, the amount of re-radiation is proportional to temperature times temperature times temperature times temperature times temperature. Fourth power. In degrees Kelvin, minus 273, but that's just mathematics. So these red sort of regions re-radiate massively more heat than these cool, moist areas. Physics, you can't escape it. And this is really profound, and we've never talked about it. Because with this re-radiation, we do two fundamental things. The greenhouse effect is really driven not by how much CO2 is in the air, it's part of the effect, but the greenhouse effect is driven by how much re-radiated heat is absorbed by gases in the air. So there's three variables. You can put that down here. Three variables. One is, the dominant one is how much re-radiation. The second one is how much water vapor is in the air, because that's 80% of the greenhouse gas effect. And the third one is how much CO2 is in the air. So this is 80% of the gas effect. This is about 11% of the gas effect. But by far the most critical thing is how much re-radiation comes up. So, it's provocative, but it's a physical reality that we can turn down the greenhouse from high to simmer by simply cooling the surface, by stopping this re-radiation of heat from the surface. We've purely concentrated on the 11% heat absorption capacity of the CO2 molecules. We know all about the water vapor molecules, but we've made the assumptions that humans could not possibly have influenced that because it's so dominant and natural. So we've assumed that's a constant, but we have completely ignored the effect of our land management on the amount of re-radiation. This is called the Stefan-Boltzmann equation, or physics, or black body radiator. Physics 101 textbooks, indisputable. Okay? So our land management has profound effects on our regional climate, the greenhouse effect. But let's go further. This re-radiation isn't just driving the greenhouse effect, but it's creating high pressure hot air above regions, isn't it? Okay, you've got all this heat going up and you're creating a high pressure hot air heat dome above these regions. And of course, a high pressure heat dome, by physics, excludes low pressure, cool, moist air flowing into a high pressure heat dome. Impossible. I mean, high pressure flows into low pressure. You don't have low pressure flowing to high pressure. Okay? So let's, can we just clean off one of those boards? Oh, yeah, please, Okay? And so this is really fundamental to your most critical strategic advantage as India, which is the monsoon. Where would India be without a monsoon? Cactus. Totally. Okay? And if you put high pressure heat domes over India to prevent cool, moist air from the Indian Ocean flowing across India and precipitating, you're in trouble. Okay? And we were just looking through this morning. We've had civilization, the Ruttman civilization. Okay, so let's look at India. I mean, I can draw Australia better probably. But okay, so basically here we have the low pressure, moist air from the Indian Ocean. And the Indian Ocean is the world's most effective evaporation basin, generating more moist air than anywhere else because of its isolation as a heat evaporation basin. And here's your basic monsoon. But if you create a high pressure heat dome over here, high pressure heat dome, you will, by design, desertify that. Okay? Where's Rajasthan?
Somewhere there, yes.
You see? And so our land management doesn't affect the greenhouse, only affect the greenhouse effect. Our land management totally dictates the monsoon. Now, obviously, the Indian Ocean, there's a whole lot of other factors, but whether and what rain we get is going to be governed by this. And again, the evidence is in archaeology, because they're digging up the civilization. It was in a green, vegetated thing with paleo rivers. We were talking about that earlier. Here are the paleo rivers. Big paleo rivers. Equivalent to the Indus. Okay? Supporting that civilization. If we over-degrade, destroy that land surface, what happens to it? We end up with desert. We prevent the monsoon. I come from Australia. We've got all the evidence in Australia, right? Basically all the pollen analysis, we take sediment cores and lake samples, we go down to beyond 6,000 years, and there it is, Mitchell grass, casuarina, calitris, all moist tropical savanna species, and basically all dependent on rainfall that was 6 times what we're getting now. Now we get acacia, anura, nolga, and spinifex, arid zone pollen analysis. So again, we have destroyed the Australian monsoon because we used to get a monsoon as well. But we killed it by making that country red, by bare red environments. So the point is that we humans are basically major climatic factors. But the powerful thing is that we can regenerate. And it's as simple, we've written it, taken it off, as simple as regenerating the Earth's soil carbon sponge so we can get that 100 raindrops into the soil, to recharge the in-soil reservoirs, to recharge our aquifers, to make 365 days green carpet, green cover, to keep things cooler, to turn down the greenhouse effect, to protect the monsoon. Okay? Now that's all very audacious stuff, isn't it? I mean, we really are talking about sort of pretty audacious sort of suggestions. But it's all in science, it's all evidence. But more than that, Andhra Pradesh, it's all here in evidence on the ground. Dry season, monsoon, cropping, world-leading hard evidence. Here's a crop. I'm standing in it. You know, like it's a bit like forensic science. Yes, there's the evidence. Of course we can have to explore and explain it, but we can't deny reality. It's there. And if we do that understanding, and then we've looked at these extension strategies, it has profound significance for global food futures and stability. I wanted to go through a little bit more because we talked about climate change and, in a sense, looking at some of these natural, safe cooling options for the climate. Okay? Very important. Now, but in a sense, it complements this whole hydrology, but from our earlier discussion, hydrology, water's the guts of the game, right? We've got water, we've got life. But this cooling climate also comes into it. 50 years ago, we had an American scientist, Charles Keeling, who drew a Keeling curve, right? Climate change, CO2. This is CO2, and this is going time. And basically, CO2, we all accept, has gone up from 280 parts per million, this is to say 1750 AD, and it's now 410 to 416, depends what season you measure, right? Parts per million CO2. So CO2 has been going up, no question. And of course it's been going up because every year, particularly in the Northern Hemisphere, we have emissions, and then we have drawdown every spring and summer by the residual green vegetation, right? And Charles Keeling, yeah, no argument about this, it's really actually fact. So we have emissions, and then that's offset. But every year, I've not drawn these to scale because I'm trying to highlight this. Every year we have about a 10 billion tonnes carbon per annum deficit. And it's because of that annual deficit that, of course, CO2 is going up. But the important thing, again, that we haven't looked at, we just looked at, okay, we have fossil fuel use, which is, again, about 8 billion tonnes of carbon per annum. And we've sort of said, hey, CO2 is going up because we're using fossil fuels, 8 billion tonnes carbon. If we stop using fossil fuels, we'll offset most of that 10 billion tonnes. The trouble is, we stop using all fossil fuels, and no one's saying we don't have to reduce our use of fossil fuels, but if we stop using all fossil fuels, we're going to have to ask for volunteers. Okay, we've got people here, hands up who want to die. Because we're going to have to ask 80% of humanity to say, hey, yeah, I can't be supported. Because we've used fossil fuels in our industrial ecology to support our whole, our whole industrial ecology. So it's not that easy saying, oh, we're not going to have emissions from fossil fuels. But that's only 8 billion tonnes, because all up there's 130 billion tonnes of emissions every year. And every year there's 120 billion tonnes of carbon per annum that are drawn down by the residual remnant green. Okay? 8 billion tonnes from fossil fuel emissions, 130 total. There's more emissions from forest fires than from fossil fuels. There's more emissions from the 2 billion hectares of grasslands and crop stubble that burn every year than from fossil fuels. But we've ignored those because we sort of said, oh no, that's nature's problem. You know, we've externalized those to nature. So we just have to take responsibility for fossil fuels, and we say, oh, well, we'll worry about that in 2100 when the models give us, you know, due confidence. We just externalize it. You know, kick the can down the road to say some politician 2100 can worry about that. But basically there's more emissions here, fires, but those fires are our responsibility. They're killing us. Australia's burning, California's burning, Portugal's burning, Canada's burning, Siberia's burning. Hey, it's us. And we can take that forest fire fuel, the thing that's burning, and we can turn it into soil carbon sponge. By just taking the fungi that naturally broke it down to accelerate the biodegradation of that fuel into stable soil carbon, into sponge. So this CO2, this CO2 isn't a pollutant, it's just a symptom, okay? And it's also the resource, because it's a resource that we need to put back into our soil to build the sponge, to give us the hydrology, to give us this whole cooling system.
Just one question on the 130 that you have over there. You're attributing most of it to these forest fires.
No.
But there is also transpiration, like you mentioned. So
respiration.
Respiration. So
Absolutely. Let me
so the
finish,
CO2 was water.
No, sorry. Absolutely. I didn't say most of it's fire. I'm saying about equivalent. So there's about, again, 8 billion tonnes from forest fires, and there's about 7-8 billion tonnes from fires. There's landfill emissions. There's cement production emissions. There's a whole lot of other emissions, and absolutely. A lot of it is respiration. Nothing wrong with respiring, because we'd all be dead if we didn't respire. Life uses sugars, and in the process exhales CO2. We exhale 1,000 parts per million CO2 with every breath we put out. And nothing wrong with it.
And how much is from plant life?
Let me come to that. So basically, yes, there's a lot of emissions. Yeah, definitely. There's some 60, 70 billion tonnes from respiration. But this now answers your question. But there's also 120 billion tonnes of drawdown by photosynthesis, the residual green photosynthesis. And we've talked about, hey, we've only down to 25% green. We're missing out on 75% green. The pre-monsoon dry season cropping said we can do it. Okay, so theoretically we can say, look, here's 120, this is on the residual biosystems. If we regenerate biosystems, we can increase that. We have to basically get 10 billion tonnes more net drawdown. That was Paris, right? Zero net carbon emissions. Actually, we've got to do more than that. We've got to go negative. We've got to draw down 20 because we want CO2 coming down eventually. But the point is, by increasing the area, particularly the longevity of green growth, you know, we can go from 120 to 180. No problems. Going from 120 easily to 180. Okay, so we can draw down carbon by increasing the resilience, the productivity, the longevity of green growth of these biosystems. But to do that, we need water. To do that, we need the soil carbon sponge. Okay, and so really that's where, again, water is the key. So this is, in a sense, the climate dilemma. And we basically, so far, IPCC very much focused on that fossil fuel, 1-2 billion tonnes a year emission reduction target. Quite frankly, it will do nothing to the big picture because it's 130, 120. But we can basically readily manage these things through this land regeneration, dry season, pre-monsoon cropping, extended longevity of green to pull down at least another 20 billion tonnes of carbon per annum. And that, in a sense, again, is the dividends from what you and India are demonstrating is practically possible. And if we put that carbon into the soil, then we get a whole lot of other dividends. You see, because if we put now carbon and we have a sponge, just say we've got a tree and we know that that's transpiring, then we know that this is cooling the surface because it takes 590 calories of energy per gram for that water to go from liquid to gas. So we can cool regions through this transpiration. Again, we set the parameters, or we set the context of what we're doing because we've got global warming, haven't we? And what's global warming? Okay, very simple. Again, we have a planet, we have sun coming in. The sun's bigger than the Earth, but of course it's a long way away, so that's why. And basically we're getting 342 watts per square metre at the top of the troposphere. And that's the incident solar radiation coming into the troposphere. And for a balanced climate on the planet, all through the last billions of years, we've had 342 watts going back out. Okay? But what's happened, we've disturbed that. We've enhanced the greenhouse effect. We've actually, sort of thickened that greenhouse effect. And now we only have 339 watts per square metre going out. And we have about another 3 watts per square metre being retained in the atmosphere. And that is global warming. Okay? What it's telling us, though, that this 3 watts is about 1% or less than 1% of the incident solar radiation. Because it's important to put things into context. And so here we have a tree that's transpiring. The residual vegetation, the residual transpiration on this planet is taking about 85 watts per square metre from the surface back out to space. That's about 24% of the incident solar radiation in energy terms, right? The current transpiration of water from soils into the air, 24% offset. So if we just increase transpiration 4 to 5%, we could readily offset this 3 watts per square metre. Again, we could just negate global warming by 4 to 5% increase in transpiration, which is here, transpiration, 590 calories per hour. So by just extending pre-monsoon, dry season cropping, these crops, by just keeping things green and living, we can cool that. It gets much better than that, because this now goes up as water vapour. When it's cool, this will form these hazes. This will nucleate around the aerosols, and of course these are actually very dangerous humid hazes. And yeah, this is what causes that humid heat stress that lots of regions are now being impacted by. And we've got to get rid of those humid hazes. Delhi has to get rid of that humid hazes, PM 2.5, PM 10, near the aerosols, so 95% humidity. That's what you've got to get rid of. How do you get rid of them? How does nature get rid of them? Easy, simple. No, we just a little bit. Just making space. I'm sorry if I'm a bit untidy here, it's okay. Again, how does nature get rid of these humid hazes? It basically turns into these things. Clouds. High albedo clouds. When we do that, what happens? These clouds, they're high albedo, they reflect incident solar radiation directly out to space. 50% of the planet naturally is covered in cloud. They reflect 120 watts per square meter back out to space. Okay? So a 1 to 2% increase in cloud will actually offset the 3 watts per square meter, even if you don't count this. Okay? So simply turning those hazes into clouds can do that. And of course, how do we do that? To do that, we need these things called precipitation nuclei. Now, we don't want to go into all the physics of that because it's a bit complicated, but it's what we did with cloud seeding, right? Now, when we use nuclei, either dry ice or salts or silver iodide, to actually cloud seed. But the most important thing there, that exists naturally, are extremely hygroscopic bacteria. And these are bacteria that have got enormous water suction capacity to suck in these humid haze microdroplets. We've done cloud seeding research in CSIRO, and basically these were 100 times more effective than dry ice and silver iodide at cloud nucleation. These hygroscopic bacteria form in the canopy of certain trees, certain forests. And again, we've got this profound thing that we know that trees need rain, but now comes a proposition that rain needs trees to form this precipitation nuclei. Clouds need trees. And we've got very, very sophisticated understanding now that, okay, these clouds form over forested areas, they'll form over here, but no, they're not going to form over here. Okay? So our deforestation has caused changes in that whole hydrology of the atmosphere, cloud formation, cooling. Okay, and then it goes further, because once we have clouds, okay, the same precipitation nuclei then of course turn those clouds into rain. And of course we need that rain to recharge our sponge, don't we? Okay, so that's in a sense nature's hydrological cycle. And it's cooling, 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 giving us rain, giving us sponge, giving us longevity of rain. That's how nature made India. Made it, this verdant green, this monsoonal paradise. But what we've done is we've turned 75% of it red, or worse. So we have agency. We have an imperative. And that agency is very simple. It's our soil. Okay? We manage the hydrology of our landscape through our management of our soil. We manage that soil through putting carbon from the air, the symptom, thinking of the symptom as a resource, and taking that symptom and putting it into the sponge to rebuild the soil, through the sponge to rebuild that hydrology. We can't control the sun. We're playing around or pretending we can control CO2. We can't control nitrogen. The only thing we control is our land management, our farming practices. And through that, we can rehydrate, regreen the landscapes, we can meet our food needs, we can address the biofertility, the nutritional integrity of our food, we can underpin the preventative health of our communities, both in terms of pulmonary diseases, humid hazes, pollution, but also basically nutritional integrity of the food. And basically each of the 17 Sustainable Development Goals that we've been set, or not we've been set, that we have set in the United Nations globally can be met by regenerating the Earth's soil carbon sponge. So look, I'd like to just leave it there at the moment, but really the big thing is having the interrogation and all the questions, and we know enormous amount. All of what I've talked about is peer-reviewed, published, hard physics. But what we've done, we've stepped out and looked at it in a new context. And none of this Keeling curve, I mean, we've known about that for 50 years. It's all IPC documented. But we just changed the mindset to say, here's a resource. What did nature do? How do we use it? Can we use it to rebuild? So look, let's have those discussions. And yeah, thank you so much for spending the time listening.
Thank you very much. Just 1 second. A hot cup of tea and then open you to this position. You can do that. You can take that in position sitting down. Thank you. Yes. Let's make it short and introduce.
Very short, sir. I just wanted to know.
Introduce yourself.
Yeah, my name is Neeraj Sinha. I work as an advisor in the NITI Aayog in the Science and Technology vertical.
Yes.
The Science and Technology group. So I just want to know this very interesting theory that you showed on the sponge formation and the 100 number of drops of rainfall falling, 99 actually falling on the earth. And in the case of global warming, that 99 going down to 17.
Yes.
How much of this work is actually experimentally validated?
How much of this work is validated, right? Yes?
Experimentally validated. I mean, so the theory sounds very plausible, but do we have any experimental basis for making these
yes, thank you
figures?
Thank you very much. Absolutely verified. This was work done by the Australian Academy of Science way back in the 1970s. The whole water budget, what happens to that water in Australia, right? It's been, again, because we've been in extreme drought, it's been reviewed recently again by CSIRO in their water planning, as well as in our Murray-Darling Basin Water Commission, which was looking at the whole irrigation of the basin. So yes, absolutely verified, absolutely documented. As I said, it will vary a little bit from country to country, but the principles are the same because the same physical processes of the sponge and what have you still apply.
So next. Yeah. Hi, sir. So Satvik, work in the governance vertical out here. So I wanted to know regarding the sponge. We have in India, like over the last 3-4 years, many instances of urban floods.
Yes.
And a lot of that has to do with the runoffs that you're saying.
Yes.
So creating sponges in the soil is one thing, but like where we have already concretization.
Yep.
What do we do? Because in cities let's say cities like on coast in India, Mumbai, Chennai, space is limited. Migrants are coming in.
Yes, yes.
What do we do about the concretized land? How does
Okay.
the sponge take place out there?
I come from Australia's capital city, Canberra, and basically it's fairly innovative. And yeah, we have a program of porous pavement. So how much of our land surface that we now put under concrete can we put under porous pavement? Being a bit radical here, we have porous plastic pavement. We take waste plastic, and you produce thousands of tons every day, and we make a open porous matter, that filtered matter, that plastic. We lay that over aggregate and allow water to infiltrate, recharge, while still having a stable surface protecting. So playing fields, footpaths, parking areas, vast areas. We also have a vast movement in urban agriculture, okay, where basically every courtyard, balcony, rooftop, people are putting soil and sponge and infiltration. But lots more detail, but the solutions are there.
Anybody here from urban planning, vertical living? It's a good one to pursue. Start porous pavements. If you have experiments. You raise your hand and I know whom to call in that.
I'm Aruna. Hi, I'm Aruna Ghosh. I'm the CEO of the Council on Energy, Environment and Water, and we also have ongoing projects going on with CSIRO right now. I have a question about the climate change part of your presentation. First of all, many thanks for a brilliant talk. Oceans absorb 90%
Yes.
of the heat on the Earth's surface. Your entire presentation is about land, and in fact, as humans, because we don't dwell in oceans, we fixate on land.
Yep.
And the ocean's absorptive capacity is 16 times than what soil vegetation permits us to. Question for you, is through your method, does it reduce the amount of ocean absorptive capacity that is needed, because that's resulting in more acidification in the oceans, particularly say around the Great Barrier Reef in Australia. So how does it balance off or ease the pressure on the oceans, if you have done any calculations in that?
Right. Look, again, scary, isn't it? 93% of the extra heat on this planet, the 3 watts per square meter, is being absorbed in the Earth's ocean. They cover 71% of the planet. We've only got 29%, which is land. And so there's no way, as the oceans warm up, they will re-equilibrate heat. So we have heat waves coming that we don't even want to think about because of that ocean re-equilibration over time. We're just in a lag phase at the moment. We're just being deceived. But what we're talking about is actually taking the 3 watts out. We're talking about reflecting the heat back out to space. We're actually saying, look, can we actually turn off that extra heat that's heating the oceans? Okay? Now, I agree with you. What it's all about regionally building resilience, buffering, cooling capacity. Canberra, again, where I come from, we have an urban forest that's transpiring. It's 12 degrees centigrade cooler in the summer's day than the nearby 3 kilometres away concrete areas. So here is a resilient, urban, cool biosystem because of these processes. The question is, yes, if we do get heat waves, how good is the buffering? But certainly it's a lot better than not having any buffering. The other thing that we mentioned briefly, the oceans also absorb a lot of the CO2. There's 38,000 billion tons of carbon dioxide involved in the Earth, dissolved in the Earth's oceans. And of course, as we try to draw down CO2 or stop emissions, some of that will just re-equilibrate back into the atmosphere. So it will take centuries of drawdown before we effectively change the CO2. So there is no way we can manage climate through just CO2 reduction. We need to go into hydrological cooling 365 green.
Yeah, I'm Bruno, an economist from CSIRO based in Delhi. I have 2 technical questions. On NIIS, you see the production of biomass, and we have to document if it's coming from inevitable water in the soil or humanized harvest.
Yes.
Imagine it is from inevitable water in the soil, in the long run mostly.
Yeah.
In the long run, is there a risk of exhaustion, of mining water? This is my first question. And my second question is, what you explained looks like also what in France the 4 per thousand initiative, where we store water. Okay. The thing is, this process is, we need a lot of literature after this French 4% 4 per thousand initiative in the soil. There was local literature, and some say also it's only for 10, 20 years. I mean, there is a carbon maximum capacity for storing. So how long in the long run also is this work?
Okay, look, first of all, as far as the water it's gone now, but the water around us, so that water that makes that pre-monsoon crop, gives it that extra 10, 11,000 tons of water, is partly from soil films, but it's not a lot. I mean, like these are just films around the soil. It may only be 10, 20% of the water. Most of that water, we believe, is coming from harvesting from the air, but that's what we're, in a sense, busy verifying, because we want to be able to answer your question precisely. As far as the 41000, totally involved, 2015, applaud you. But the point again, this is so important, it's not just about drawing down carbon. That's not a solution. We have to build the sponge, we have to build the in-soil reservoirs, we have to rebuild this hydrological cooling. Because we can put tons of carbon, store them, but it's not going to change the climate. As we just talked about the oceans having so much re-equilibration. It's only when we rebuild the sponge, the hydrology, these cooling process, 365 green, that we will get these positive feedback multipliers in hydrological cooling.
Thank you.
Hello, sir. I'm Richa. I work as a young professional in the urban vertical of NITI. So I have two questions for you, sir. One, what is the minimum land area required for this sponge to make a quantifiable difference? And second, how much of the urban heat island effect can be offset by using the sponges in the urban areas, and especially the pavement that you mentioned?
Okay. What is the minimum area? Well, that's depends what the target is, where you are, but basically we're getting effects from farming effects from relatively small areas, right? So re-establishing 1,000 hectares of rangeland forest changes the microclimate pretty dramatically at the agricultural landscape. As I said, in an urban forest situation, it's much, much smaller. 100 hectares, of region will create its own microclimate. The real question is, I suppose, it's a bit philosophical. Every square metre adds to it. So how many square metres do you have to add, right? So that's really the important thing. It's a bit like the old Chinese proverb. When is the best time to plant a tree? 20 years ago. When is the second best time to plant a tree? Now. And the same thing applies here. As far as your effect on urban heat islands, yes, we can totally offset the urban heat island effect through these hydrological urban forest porous pavements. It's simply a matter of getting rain that falls into our soils, helping that transpire, every gram 590 calories of cooling.
Okay. You start a campaign on forest pavements.
My name is Jehne Kumar. I work for, is it working? No. I work for Climate Bonds Initiative, and we are mainly exercised by the question, how do you finance these transformations, basically? In India, in fact, we are looking at mobilizing capital for resilient agriculture. So that's my introduction. I had a couple of questions. When you talk about land management, agriculture is one story. Agriculture is one story and a very important part of the whole story. But we've also been hearing that afforestation campaigns are extremely important.
Absolutely.
And I'm just thinking that in agriculture, you said that natural farming techniques lead to what you're calling, water conservation to a high degree. Then would you then also say that correct practices in afforestation also will make that difference? And in agriculture especially, while the content of soil organic matter is fortified multiple times, but it's crop agnostic. So when you fortify, would not different crops need different kinds of minerals? And the question is that simply soil organic matter increase in the soil. How does that cater to the different nutrient needs of different crops?
Right. Look, let me break that down. First of all, as far as what is the cost of this, and the cost is no cost, because all we're doing is doing less damage, less inputs, because answering the last part of it, see, basically we're increasing the availability of the nutrients that are in that soil naturally by creating the sponge. We're massively increasing the surface area exposure. We're massively increasing the cycling efficiency of those nutrients. So basically, we're not adding nutrients. We don't need to add nutrients, right? Because by increasing their availability, we can increase biofertility as in a rainforest. So most of these practices, they're profitable because we've got lower input. We don't need to cultivate as much. We don't need to fertilize as much. We don't need the biocides to kill things. Okay? So these are savings. So the farmers are getting the same yields, but often much, much more reliably, with higher quality and lower inputs. So all the economists, this is return on investment, This is strategic capital. Okay, the other point about afforestation, absolutely. We are 100%. We're not really saying it's just cropping or grazing. This is an integrated land management regeneration, and agroforests and shelter woods are a critical part of it because they're things that stop evaporation. The deep tree roots are nutrient pumps, bringing more nutrients from subsoils, cycling them into the top. They're habitats for animals, they're habitats for dust collection, and they are the drivers for the humid haze and water harvesting. So no, look, it's an integrated agroecology, trees, plants, animals, a wonderful regeneration, revitalization of opportunities, all tailored to local conditions.
Hello, Ajit Pai, NITI Aayog, I look at economics and finance over here. So just going back, it's a related question to the one that was just asked, but when we are looking at the reason why 75% is red, a large part of that was the rollout of agriculture globally and the deforestation.
Yes.
So today, when we look at what you're proposing, most of what you've talked about in terms of the math for transpiration, all of that is with trees.
Yes.
So are we looking at, is there a big difference between an orchard in terms of how much it's contributing relative to traditional agriculture, which is basically the grains and the cereals? And is there a possible shift back to more forest or trees contributing much more to a diet than...
Right. I don't think we have to change our diet, but what we certainly are talking about is reintegrating trees into protective, sheltered, resilient agro-ecosystem, right? From, as we said, the evaporation, because the desiccation without the winds, without the trees, but also that water harvesting, the nutrient cycling. But we're still going to be eating, from crops. But in Australia, what we're doing now, we've got, in a sense, alley cropping, where we have alleys of trees, like corridors of trees. We've got zones between the trees. And what we're also doing, and India may want to look at this as well, we're going back to nomadic concepts. So when there's enough rain in a region, yep, we can come in there and we can crop those soils, those laneways between the trees, but we might only do that 1 year out of 3, 1 year out of 4 when there's rain. The rest of the time it's still staying green, we're still grazing it ecologically, but rather than having, in Australia, 25,000 hectares of cropping land that we crop till it's dead, we can now say, look, there's 150 million hectares of opportunistic cropping in grazing when it's suitable.
Hello. Ashok Kumar, National Water Mission Director. I was something similar to that what you was about to ask. India has grown, the agriculture has expanded a lot. So area under cover of agriculture has increased. So whatever your green you are telling it, yes, has increased. And that too, mostly paddy, it has come up. But the other effect of it was the overflooding and the lot of drawal of water from the ground. Yeah. Which has in turn made many places sort of desert. We can give you a classic example. Punjab has, state of Punjab, out of 139 blocks, 108 blocks are overexploited. Yes. And paddy is the cultivation. Yes. And what is the suggestion? Is this paddy or crop or trees? I mean, that's what it do suggest that for this process, trees are better. Cut down the cropping and sales and go for trees.
Yeah. Look, I'm not saying, I'm not prescribing trees are better. But the message is we are relying on irrigation from those 2 drops and the groundwater. That's coming to an end globally. So it's very rapid that we have to rethink and say, no, we need water from the 100 drops in the sponge, in the in-soil reservoir root zone, and we have to, in a sense, become less reliant on irrigation from these outside sources and much, much more water use efficiency conservation in those biological soil layers. When we do that, we can progressively start recharging our aquifers. It might take several decades, but we must do that. So it's not, but I agree with you, the 108 out of the 130, whatever. That model, we have to find a new solution.
I am Avinash Mishra, Canadian Water System. Actually, the water is stored in the carbon form.
Yes.
So the quantum of water is fixed because it will vary from zone to zone. And accordingly, the cropping pattern will also vary because there would be the natural crops that needs to be grown instead of intensive cropping and intensity of irrigation. So that will result in the threat to the food production of the country. So how do you feel? Should we have a gradual transition from towards the carbonous fund from what we are having the big dams, or we should just go for the smaller water bodies and thereafter gradually towards the carbonous?
Yeah, I can't answer that because that's really India's strategic sovereign decision, right? It's not my role to talk about that. But really, the bottom line is just doing it. And hectare by hectare, farm, region by region, just doing it. And as you do it, you become less dependent on these dams and other bodies, right? And there's no harm, there's no negatives. But really, the point I want to make, the pre-monsoon dry season cropping, what those innovators in Andhra Pradesh have shown that on what is traditionally 100 millimetres of rain, they are able to get a crop, which basically, if we extend that strategy, that biological water harvesting strategy, yeah, we've got a 10-fold water use efficiency.
From what I've understood, if you first start covering your arid, semi-arid, desert areas with pre-monsoon dry season cropping, increase the green cover of the soil with all its beneficial impacts to improve the water, contain water absorption, and then you slowly move, and that's what will happen. So
we have to use appropriate crops.
Appropriate crops is of course very important. Anybody else? Yes, please.
Sir, I am Shwetal Shah from Climate Change Department, Government of Gujarat. My question is little similar to previous questions. That is how we should start implementation of this concept, and what incentive shall the government offer to the farmers or the community to make this popular, and what sort of training things we should do?
You will accept that it's a little unfair to ask Professor from Canada about how we implement it in India. Thank you for asking that, though. We create a group within NITI Aayog then to talk about implementing it across different states, because every state is in any case different in our country. So we'll take it forward from there. And the first workshop will be held around towards the end of February. And will be most welcome. Yeah? I don't think it will be. Yeah? Anybody else? Yeah? Do you want to ask something?
I think it's more or less covered. Sir, I'm Arunima Chandra. I'm a young professional at the Water Resources and Management Institution at NITI Aayog. So, would you have any suggestions as to the change in the macro level land use patterns of the country so as to reclaim the red zone into the green zone in the light of urbanization, population increase, and different purposes for which land is supposed to be allocated? And also in the light of different soil varieties that we have in India.
Right. Again, it's a little bit difficult, but let me say, from my understanding, there is a lot of land in India which is, in a sense, not wasteland, but not fully productive. For example, in forestry, we've told that there's in different regions, 17% of the land is forest, but only 3-5% is highly productive. So there may be a significant area of land which is underutilized. And you start at that wasteland because you're not taking food up people's livelihoods, and say, how can we actually make that healthier, more productive? And then you can document, here are options, here are viable, practical, profitable options, and then farmers will say, I will try that. And I think the experience has been very rapid. where here are farmers are saying, look, here's a 12-ton mixed cover crop pre-season, and whereas there were 10,000 farmers looking at that year one, by year two there's 50,000 farmers. But they are empowered, they are making their strategic decisions on their economics. There's no imposition. But in the wasteland area, there's an enormous amount of benefit we can do. This is wasteland, how do we lift its resilience, restore it to benefit the whole of India.
Last question.
Thank you. I'm Sophie Poisot from the FAO headquarters. In the FAO headquarters, we take this kind of findings very, very seriously. 14% of global population suffers from water scarcity, and we see increasing conflicts and migration from degraded areas and dry areas. So 3 weeks ago, after a report at our World Commission on Food Security, this is a committee that gathers all our member countries to discuss how we feed the world, basically. Examined the report on agroecology, what we call agroecology, which is a family of approaches about farming naturally, natural farming, and yes, we have reference from India in that committee. And basically the conclusions from our membership, all the member countries, was yes, we really need to look into these natural farming approaches as a restoration of ecosystems, of the security, etc. So this is happening around the world, and we're looking at India as one of the examples actually of how you can on a massive scale implement this regenerative farming. My question to Walter is, you started from the fungi and the microbes and their role in creating this regenerative system. Can you say a bit more about how that works and how natural approaches can biostimulate those microbes?
Yes.
How are they activated?
Look, this is very important because as in nature, it is these microbial, fungal symbioses that are driving these changes. And all we need to do is switch them on. See, we're not adding nutrients, we're not adding anything magical. We just say, here are the natural processes that nature used 420 million years ago. They're still in our soils, but they're often very, very suppressed. And all we have to ask the question, what is limiting them? Can we take those limitations away? So we're not adding anything magical. We're just helping nature restore these processes. How? Oh, okay. And so, that's getting detailed. Yeah.
That's a completely different subject, and we have had 2 or 3 meetings here on zero budget natural farming, and and we've been pushing it for now more than a year and a half and so on. Vijay here is, and we will have that. We combine the two. That is the other part of it. So let me bring this to a close. Everything has to end, unfortunately. So, profound thanks.
Thank you.
And really, you opened our completely new vista for us. But I think the best thing to say is that you've given India a chance to lead globally. We can do it.
Absolutely.
And therefore, I think that's a very exciting prospect. I promise to you that we in NITI Aayog will persist with it, will pursue it. I have had already a wonderful volunteer, Mr. Ashok Dalwai, who heads our rain-fed agriculture authority, and that's just the right thing, right agency to do it. He'll convene, as he said just now, the workshop at the end of February, and we will then put it together. And there's my young friend here, Aditi from NITI Aayog, who will join hands with it.
Yes.
And we will take it forward from there.
Thank you very much.
Thank you very much. And look forward to further interaction on the ground and improving the evidence which is already there, which is what we need to do. So thanks a ton.
Thank you very much.
Thank you all very much for being here. Thank you.